This is the last lesson of the sounds topic and is called Comparing Waves. There are three learning objectives. First of all, compare longitudinal and transverse waves. Secondly, recall that all waves can be reflected. And finally, to explain what superposition means.
Waves are created by the wind blowing over the surface of the sea. Wind is moving air. Some of the energy stored in the moving air is transferred to the water. The greater the distance of water over which the wind blows, the bigger the waves when they reach the coast. In the British Isles, strong winds often blow from the southwest. Waves will have travelled for thousands of kilometres across the Atlantic Ocean, getting bigger all the time as more energy is transferred to them. Beaches in Cornwall facing the Atlantic Ocean are great for surfing because the wind has travelled all the way across the Atlantic Ocean, making the waves bigger and bigger. However, beaches on Cornwall's south coast do not have such good surf because the winds blowing onshore have covered much less distance across the English Channel. It may seem that a wave is water moving towards the shore, but it is not the waves making the surfers move. The surfers are actually surfing down the waves. The waves lift the surfers up, so they store more potential energy. This energy is transferred as they slide down the waves. Look at the seagull floating in the ocean as the waves pass by. The seagull bobs up and down, but it is not moved forwards by the waves. Waves move up and down as the energy passes through them. Waves do not transfer water.
The ripples in a pond in the picture are small waves on the surface of the water. They spread out from the diving duck in the centre towards the outside of the pond. And the waves, as you will recall, are transferring energy. If we could zoom in on the water and look at the individual molecules of water as a wave passes, we would see that they move up and down. They do not move horizontally. And this is easier to see if we just change the colour of one column. Those particles are moving up and down. The wave itself is actually moving across from left to right. So the two directions of the wave and the particles are at right angles. So the water particles move vertically up and down, but the energy, which is the direction of the wave, is moving horizontally across the surface. That means that the ducks are not actually pushed outwards by the ripples, but they simply bob up and down. Water is a transverse wave, and that means that the particles move at right angles to the direction of the wave energy. Transverse means across, and the direction that the water molecules move in is across the direction of the wave. Sound, on the other hand, is a longitudinal wave, and that means that the particles of the medium, which is usually air in the case of sound, move back and forth parallel to the direction that the wave energy moves. So the particles move along the same line that the direction of the wave moves in. Let's have a look at sound, which is a longitudinal wave. In this animation on the left, we have a vibrating guitar string, say, and as it moves backwards and forwards, it bumps into air particles and pushes them into other air particles. They vibrate backwards and forwards, creating areas where there are lots of air particles together and other areas where they're further apart. There's a similar demonstration here with a tuning fork, which creates waves of sound, and the tines of the tuning fork are actually moving backwards and forwards. They're bumping into air particles. Those air particles move backwards and forwards, bumping into other air particles. And you can see that there are rings there where air particles are close together, and there's spaces between them where the air particles are further apart. These are actually called areas of compression and rarefaction. Compression is where the particles are close, and rarefactions are where they are spread out. The questions to recap, just check you've been listening carefully. First of all, what is the difference between a transverse and a longitudinal wave? The answer is that in a transverse wave, the particles are moving at right angles to the direction of the wave. In a longitudinal wave, the movement of particles is along the same direction as the wave. Question number 2, which way will ducks on a pond move as waves pass them? The answer is that they will bob up and down. They do not move across the surface. Okay, I want to talk a little bit about the amplitude of waves. We've come across the word amplitude before. It is the distance from the starting point, which is the middle of the wave, to the crest or the trough of the wave. So if we're talking about water, it's the distance that water moves from the middle to the top or from the middle to the bottom. You'll notice that the particle movement actually is twice the amplitude because the particle moves both up and down, but it's a common mistake that people make. The amplitude is only half the distance from the top to the bottom. It's the distance from the middle to the top or the middle to the bottom. The amplitude of waves on water gets smaller as the waves get further from their source. This is because the energy transferred by the waves gets more spread out. If we look at this, the ripples created when this stone is thrown into the water, you'll see initially there is quite a high wave, and as it spreads out, it gets shallower and shallower and smaller. Some more questions then. If you drop a stone into a pond, what happens to the energy that was stored in the falling stone? Some of it gets transferred to sound. What happens to the rest of it? Well, the answer is that energy is transferred to the water. That's what makes the water particles move and creates the wave. And that energy is then spread out across the surface as the wave gets bigger and bigger and more spread out. Secondly, how could you make a wave with a bigger amplitude in the pond? I hope that's fairly easy. You just drop a bigger stone, a heavier stone into it. It will have more energy and therefore more energy will be transferred to the water. Question 4. If you have a look at the picture there, which duck will bob up and down least as the waves pass it? So have a think about that. This follows on from the previous question, that the waves are getting smaller as they get further from the source. So therefore the duck furthest from the center of the ripples will bob up and down least, because as the ripples spread out, there's less energy in each section of the wave, so the amplitude will get less. Okay, so we're moving on to our second learning objective, which is that all waves can be reflected. And if a property is true of one wave, it is true of all waves. So let's look at reflection of waves. Waves can be reflected. In the film here, this is a ripple tank, and it's a setup that produces waves. And you can see a straight wavefront moving from left to right. There is a barrier, which is the black line in the middle, and that reflects the wave back the way it comes. What about if the barrier is at an angle? In this case, you can see that the water wave is reflected at a different angle to when the barrier is straight on. And if you watch this again, see starts to reflect it up the screen. And if you look at those two angles are always equal. This is exactly the same as with light. When light is reflected off a mirror, a straight mirror, then the angle of incidence and the angle of reflection are always equal. So the angle's changed, but they're both equal. If we look at multiple waves, then reflecting here, what's happening is the waves moving from left to right, but they're being reflected upwards. And we get what's called a wave interference pattern because the waves are moving through each other. And we'll look a bit more at that in a minute. So light waves are reflected by a mirror, sound waves are reflected by hard surfaces, water waves can be reflected by a barrier. All waves can be reflected. And here's a picture with a very nice photo showing the waves made by the wake of the boat are actually being reflected off the barrier there. Learning objective 3, and that is to explain what superposition means. So, as we saw in the previous film, waves can pass through each other if they're going in different directions. And as the waves pass each other, their effects can either add together to make a bigger wave, or they can cancel out the wave altogether. This is called superposition, which literally means one wave is on top of another. So if we look at the diagram here, and at the top we have two waves meeting each other, and the crests of those waves and the troughs are both in exactly the same position, so that when they meet, the wave is twice as big. The amplitude is twice that of the two waves meeting. If you look at the bottom, however, one crest is matched up with one trough, and in which case these have an opposite effect and they cancel each other out. Question number 5. People in small boats need to be careful if they're sailing near cliffs, because the waves can be bigger than in the open sea and may be coming from more than one direction. Why do you think this is? Well, the answer is that the waves can be reflected by the cliffs, so they could be coming from the direction of the sea and from the direction of the cliffs. Some of the waves also may be bigger, because if the peaks of a wave from the sea and the peak of a wave from the cliff occur together, their effect will add up to make a bigger wave. Question 6. Look at the two pictures. The first one is of sound waves and the second one is water waves. The question is, do sound or water waves get smaller faster as they spread out from their source? They both will get smaller, but which will get smaller quickest? Well, if you look carefully, the answer is the sound wave, because the sound wave spreads out in 3 directions through air, but the water wave only spreads out in 2 directions across the surface of the water. And that means that the energy in the sound wave is spread out more quickly. Okay, well, that's it for now. And again, as usual, I'd like you to do the recap quiz. Make sure you've listened to this lesson carefully before you do that. That will help you get the most out of it. And do at least one of the worksheets that are on the lesson. If you're particularly interested, there's something else you can do there. That's a little link. It's a short clip which explains how wave interference is used in noise cancelling headphones. Okay, so the next lesson will be a revision lesson, and then there will be a test after that. Bye for now.